Hello. Because I'm from math department, I will introduce something done by mathematicians. That's the positive mass or energy theorem in general. Oh, okay, this is misprint. General relativity. Okay. So, the positive mass or energy is the same thing. Okay, let's introduce background. In 1960, ADM made a detailed study of isolated gravitational systems. They adopted the Hamiltonian viewpoint, choosing a space-like hypersurface as the initial surface and writing Einstein's equations as evolution equations from this initial data. And after integrating by parts, and I will show the details later, they discovered the conserved quantity n of g. And it's easy to check that in Schwarzschild, spacetime mg agrees with the mass m up to constant, maybe it's the 4m, so 4 times m. So they guess that they conclude that the conserved quantity mg is total mass of isolated system. For KL solution, this quantity is also m. All right. So then ADM conjectured that the mass measured along the space-like hypersurface is non-negative, and it's zero if spacetime is empty. Now, the metric of any physical spacetime must satisfy Einstein's equation. It turns out that the energy momentum tensor encountered in real physical model satisfy called dominant energy condition. You know, in singularity theorem, this is also one of the conditions. And by Einstein's equation, if we contract the indices, we have the equivalent condition of that Ricci tensor is positive. Okay, so that's the conjecture. If Ng is a asymptotic flat, I will explain what asymptotic flat is. Riemannian 3 manifold. It's a space manifold. With no negative scalar curvature, then the mass is positive. And if spacetime is flat, the equality holds when the spacetime is flat. And the general form is called the positive energy conjecture. It's just change the condition on Ricci tensor to the dominant energy condition. Okay, so they are equivalent. So now what's asymptotic flatness is?
So n, G is the metric, and what was n?
N is a manifold. Yeah. So we can just see Schwarzschild as an example of asymptotic flat. I mean, if we have infinite space, and if we dig the center of it and look far, then the metric comes to like flat, like a Euclidean space. Yeah, we can just see Schwarzschild when R goes to infinity. We got Euclidean metric. Okay, and Herbert, Einstein, actually we already seen that in class. Okay, then we consider now that's the procedure how ADM derived the mass. Consider a family of metrics or G of t with H defined as dg over dt. And after calculation, we get this equation. Gij is the Einstein tensor, and this how to pronounce this Greek? I forgot.
Pronounce which one?
Xi or
Xi.
Xi. Okay.
So t is not a coordinate time. T is a parameter.
Yeah.
T is not x naught, is it?
No. Now it's a Hamiltonian viewpoint, so we already split the.
So you don't have a time. So
yeah.
That's the Hamiltonian time.
Yeah. So the psi j is defined as the first derivative of a metric, and we see that the boundary term is variation of a geometric invariant. Let's see if the spacetime is vacuum, then the first term vanishes. And then the second may be related to the pure gravitational field energy or mass. Okay, now let's see this partial I Hij minus partial J Hii. So we see this term in integrand of the definition of energy. And similarly, we can also define the linear momentum and angular momentum. We won't go details how they make this definition. Well, except for the Gij, we also have Kij. They are the second fundamental forms of time slice. The Gij is first fundamental form. Okay, go too fast. And now we shall give some math details that those quantities are well defined and they are conserved up to time. So we have some estimate here. The first is about the energy. When R goes to, this formula shows that the integral, when R goes to infinity, the integral is convergent. And the second one is for linear momentum. The asymptotic flatness condition, the rate of decay of the R, of the metric of R, guarantees that those two integrals are convergent. That's it.
So it's a difference between two surface integrals. And what is the integral of B prime over B?
B prime over B? No. It's R goes to infinite. So the integral is on the SR, on the sphere, and R goes to integral. Infinity. And that's what we show that when R goes in infinite, the integral is convergent. Yeah. Yeah, the difference goes to 0 when R goes to infinite. Okay, now we shall show that those quantities are conserved up to time. So that's the similar thing. Yeah, we won't show so technical details. So that's the conclusion. Okay. Now we already know that those quantities are well defined and conserved. And I didn't mention the conservation of angular momentum because they are the same. But maybe because how to say let's here now because integrand in Pi is this Kij minus Gij trace K, and the angular momentum integrand of angular momentum is just xj times this integrand of Pi. Yeah, so it has for the convergence of angular momentum, we need a bit stronger condition of than linear momentum. Yeah. Okay, now that's the positive mass theorem. So a natural question is why should we care about this conjecture? Yao, Sean and Yao, the ones who proved this theorem, one of them Yao, the same Yao in Calabi Yao. He wrote a biography of his math life, and he explained why this conjecture should be considered. Because the universe can be sort of an isolated system. The conjecture also applies to the universe as a whole. It's a pure theoretical concern. So the question was important enough to have run this special session as major GR meetings for years because it is related to the stability of space-time and the consistency of Einstein's theory itself. Space cannot be stable unless its overall mass is positive. So. And the mass difficulty is pretty interesting. they proved a couple of spatial cases first, but they think that the full conjecture is even difficult for geometer to comprehend, and they didn't believe it was true for pure geometric standpoint. Misha Gromov, who is a famous geometer, the Wolf Prize, he told them that based on his geometry intuition, the China case was clearly wrong. On the other hand, physicists thought it was true, so it's pretty useful for mathematicians to have some physical intuition to help them to solve some problem. Okay, now this is one of the spatial case of the theorem they proved, called time symmetric case. I don't know why it's called like this, but we can just introduce the sketch of the proof. So that's an assumption, some asymptotic flatness, and this is Schwarzschild plus some other terms. And
so that's just the spatial part, right?
Yeah, just the spatial part. Yeah, and scale of curvature of the spatial part is positive. Then it holds that the mass is positive, and the second part is that if fm equals 0, then matrix is Euclidean. Okay, 3 steps. So it's like using contrapositivity. We first assume we have a G with n negative, and we can find another metric G tilde close enough to G that also have G tilde, and such that the scalar curvature is positive. And they use some techniques of minimal surfaces, some nonlinear elliptic equations, and they use some math techniques to solve that. Can be used to construct a complete area, minimizing minimal surface, and then use second variation formula for area. You can show that the minimal surface in step 1 contradicts the fact that the R tilde is everywhere positive. Then they can conclude that M is positive. And the second proof of the second part,
So this is a very special metric, which depends on a function alpha. What exactly? So what is O2? Oh, it's just, O2 is just a correction of order 1 over R squared.
Yeah. I mean the order of the second derivative.
Doesn't play any role in the proof, right? Because you don't have to be specific about the O2. Just say that it is of order 1 over R squared correction.
No, as O2 is the order of the up to the second derivative.
That's what I mean.
Yeah. And the proof 2 of F, they use this how to pronounce his name, or Mukada York. This York also has there's also another mass called Brown-York mass in GR. ADM mass, Brown-York mass, and there's 3 or 4 popular definition of mass. If m equals 0 and R does not vanish identically, then exists a metric G tilde conformal to the G such that M tilde is negative. And by part 1, we can conclude we just use the conclusion of part 1. We can see that n equals 0 implies that R vanishes identically. You can see that it's direct. Okay, so step 1 is use variation method to show that R vanishes identically implies Ricci vanishes identically. It's just the whole thing. Have some condition on that. Yeah. And the second thing is that on 3-dimensional manifolds, R Ricci equals 0 implies all Riemann tensors are 0. Then the G is flat because all Riemann tensors are 0 implies that G must be Euclidean. All right. Okay, so this is just the some time symmetric case. The general case is they must solve a highly nonlinear equation called the Young's equation. Young himself is a Korean. He didn't believe that this equation has a global solution. So he gave up the research, but Sean and Yao goes on and they proved that it has a global solution, and they proved the theorem by using that. Later, Edward Witten used the spinor method from supergravity, gave a simple proof of the positive mass theorem. But we won't go to details of that. And 2 years later, Sean used techniques in proving positive mass theorem to prove a famous math problem called the Yamabe problem. It is that have a compact manifold M dimension greater or equals to 3 with a Riemannian metric G. Then we have a G prime conformal to G, for which G prime has a constant scalar curvature. Conformal is just that Gij equals to e power of some function Gij. This is conformal. Definition of conformal. All right. Yamabe made this problem because he thought that solving this problem may help to solve the Poincaré's conjecture, but it's not the case. But this problem is still pretty important. Yeah, Sean solved this, and it's the greatest math accomplishment of him.
And this Yang equation, what's the capital D there? Are those covariant derivatives? Or
Yeah, no. Covariant, no. They're just a derivative. Yeah.
Just an ordinary derivative.
Yeah.
So it's d by dxi, d by dxj.
Yeah.
Okay. And what's d itself?
D is the sum of all derivatives. Yes.
Derivative squared.
No, the sum of all derivatives. Yeah. They use this notation in PDE.
Okay.
Yeah. Okay. So the last problem is why this theorem is not so well known among physicists. Okay. I've asked some students doing GR. I asked them that, do you think that positive mass theorem is important? And they answer me, what is positive mass theorem? So let's compare the two singularity theorems, the Penrose-Hawking. If space-time in general relativity satisfies some reasonable physics conditions, such like dominant energy condition and no closed word lines, then it does not have singularity. And my private opinion is that GR has already been strictly tested. It's nothing to be astonished if it proves to be reasonable or stable. So once positive energy was proved, most physicists lose interest in it. On the other hand, the result as singularity theorems, which shows the effects of GR are worthy of more concern. That's my private opinion. Okay, so that's it. Most materials of my PPT are taken from this Yamabe problem. It's a paper here, and a math problem of general relativity. It's a book written by Chris Doyle. And the last one is a biography by Yao and that is. Thanks all. That's
Thank
it.
you.
Okay, so my name's Jim Asbrock. I'm the retired electrical engineer in class. So this is all kind of new to me, and that's why I have so many questions. But my presentation is probably going to be more of a survey than an in-depth presentation because of my background. But I'll go over basically Gaussian curvature, examples of it, and then the Riemann curvature. The 2D you have already heard about, so I may skip that. I will go over the 3D metric, the Bonatos, or the BTZ metric, and then just look at higher dimensions, and then we have time just the P-form representation of the metric. So Gaussian curvature. So I mean, this is a relatively, old concept invented by Gauss, who had to survey the kingdom in Germany, and he had to measure all these hills and came out with an idea that was invariant no matter how it was measured. And the thing that was invariant is called Gaussian curvature, and it's equal to the product of the minimum and maximum curvature of any surface. So if you have a surface, you can always draw a tangent to that surface, and then you can find the radius of the sphere or circle that is tangent at that point and come out with a radius. So those are called the principal curvatures, and the Gaussian curvature is just the product of those two curvatures, the min and max values. So if you take the surface integral of the Gaussian curvature over some region, it's called the total curvature. And if you look at the total curvature over a geodesic triangle, you come out with the observation that if the curvature is positive, like in a sphere, some of the angles will exceed pi, while if the surface is negative, it will be less than pi, or if the surface is 0, it's exactly equal to pi. So this is basically the mathematical statement of that, and basically one of the angles then is a measure of the total curvature of the surface, and this is extended by the Gauss-Bonnet theorem that basically connects geometry, which is curvature, and also topology, which is number of vertexes and edges and faces. And you'll see this referenced many times. In fact, there's an Einstein Gauss-Bonnet metric. So what Gauss basically found is that Gaussian curvature is an intrinsic property of the surface, just like distance, just like angles, and it's invariant under any kind of distance-preserving transformation. So these are just some examples, and these are just some more definitions, but the tangent, so if you have any kind of curve, you can always draw a plane that intersects that curve, and of course the tangent is a derivative of the function relative to ds, and ds here is the standard definition for the metric in 2 dimensions. You can define a unit normal to that curve, so that's the standard definition. Then you can define a curvature in terms of that ratio of how fast the tangent is moving or changing along the curve. You can also define a binormal to the curve, and then you can also define a torsion, which is in terms of the normal and how fast that binormal derivative is changing with respect to the line element or the arc length. And just giving an example, torsion, which you usually don't see too much, this would have more torsion than this because the osculating plane is rotating faster. And I just mentioned torsion because that will come up later, because it is also an invariant in geometry, and it's independent of the coordinate system that you're trying to measure. All these things are connected by the Frenet theorem. The prime here denotes the derivative of it with respect to the arc length. So they're all connected, and this is the matrix where K is a Gaussian curvature and tau is a torsion. And of course, these are all examples. Of course, the sphere has Gaussian curvature of 1 over r squared because both r1 and r2 are the same. A cylinder is 0, mainly because in this dimension, the radius is infinite, so 1 over infinite is 0. So even though the cylinder has a curvature in this dimension. In the other dimension, it's 0. So the total curvature, which is the product of the two, is 0. And then, of course, you can have a cylinder that is curved. And then these are the saddle, which has a negative curvature, a monkey saddle. Actually, the curvature is actually 0 at one point right there in the middle. Otherwise, it has a negative curvature. Toroid, which has a positive curvature. And then amoeba strip, which actually has 0 curvature, but it has this other property that's orientability, that if you take any vector, let's say it's pointed up and go all the way around the surface, it's pointing down. So that's another invariant property called orientation or orientability of the surface. Okay, this is, I think we've gone through this in class. Basically, the affine transformation is if you take a vector and parallel transport it across any surface, as you go across that surface and come back, these two things will not align if the surface is curved. And the affine transformation is a measure of that. And you can define a derivative of that, a covariant derivative, with these two properties, that the derivative of the metric is 0, and also you have kind of like a anti-commutation relationship between, it matters which, it does not matter which way you form the two derivatives, okay, that this value is 0, which means it's torsion free. So there's various definitions of the Riemann curvature, and the one, of course, we used was the deviation of the vector after a parallel transport around the path. Another definition that I came across in terms of the Levi-Civita connection was, it's kind of like the how much non-commutability there is with a covariant derivative. So as you can see here, these two things, if these two derivatives don't depend upon which one is first and second, then it's 0, but in general that will not be the case. So examples, we went through the 2D metric kind of in class, that the only two things that come out of the metric, everything else is 0, are these two Christoffel symbols. So the Riemann curvature is given by this in terms of the Gaussian curvature, and the Ricci curvature and the Ricci scalar, where K here is the Gaussian curvature. And I didn't know, but this is the 1+1 metric of space-time, and there's a whole bunch of references I found that people have come up with different things. However, they all add terms compared to the Einstein-Hilbert action, because as mentioned before, if it's just the Einstein-Hilbert action, then G is 0. So you have to add something to it, and this is just one example, and all these papers have different actions, but they have to add something to the Einstein equation, or otherwise the solution is 0. So 3D metric. One of the metrics I found that you can solve in general relativity was found by Bonatos, Teteboom, and Zanelli. So it's called the BTZ metric, and it's in basically 2+1 dimension. However, it only admits a solution if the cosmological constant is negative. Okay, so otherwise you don't get any black holes, or the black hole has a negative or complex radius. So this is the action that he uses. So it's very similar, or exactly the same as Einstein-Hilbert action, okay, except now it's only two dimensions of space and 1 dimension of time. This is the metric, and it has two variables, n sub r and n sub phi. This also applies to a rotating black hole, and these are the solutions. The n sub r depends upon the mass, and the angular momentum. The n sub phi just depends upon the angular momentum. And again, in all of this, L is 1 over the square root of minus the cosmological constant, and the cosmological constant is negative. Otherwise, you don't get a black hole. And this is the radius of the black hole solution in terms, in this. So if it's not spinning, J is 0, then you just get this L parameter times m over 2. And if you add the if you do it in terms of, this would be a G in here if G was not equal to 1. And there are other theories. There's a book by Carlip, actually. The whole book is on 2 plus 1 dimensions.
And this paper is fairly recent, right?
Yes.
Because it goes...
Yeah, and I was kind of interested in Witten has one.
10 years, this is, what, 14 years ago?
Yes, I think it's less than that. I think it was 2002, so 2002. Yeah. But I was kind of interested, the one reference was Witten had a paper on 2 plus 1. So it'd be kind of interesting to see what he said. So I tried to solve it to see how he came up with a solution for it. Okay, so basically I did the assumption of it's non-rotating, so I got rid of all the angular momentum terms, and then I used the AR and the BR representation that we did during class for the Christoffel, or not Christoffel, but the Schwarzschild metric. And then I used Dr. Hamber's program to solve the GR equation for A sub r and B sub r, and found some differences, and all of them were to do with what the constants of integrations were assumed. Okay, this, if you remember when we solved it, it was a second order differential equation, so you had 2 constants, and the C2 constant was 1. I think that comes basically from the fact that the Ricci tensor is 0, but the C2 or the C1 constant, it depends. If you remember, what we did was you have to match what gravity is in that dimension. Okay, and what we did in class was to assume that C1 was equal to 1 minus 2 GM over R, because that's what we found before in terms of Newton, that the B term here was equal to 1 minus GM over R. So if you do that, you do get a solution, and these are the solutions, okay? And actually you get a black hole radius, you get a cubic equation down here to solve. You got to solve this. And you do get a black hole, but there are other ways of doing it. And what the paper did was to assume that the C2 was a lot simpler. It was independent of R, and he assumed just equal to basically minus 1 times GM, and that's how he got his solution. And the other one that Dr. Hamber had in his program was to assume it's 1 minus 8 GM, and if you do that, you get a different black hole radius. It's basically this. But basically, all 3 approaches, you can get a black hole, and it depends upon what you assume to be the 2-dimensional equivalent of gravity. Okay, whether it depends upon R or not. So I think you mentioned before, it may not depend upon R. It may be R to the 0 power, in which case, then this would be the correct radius to use, okay? Although, again, he used, instead of a 1 minus 8 GM, or 8 G, he used just minus GM. So I don't know what.
For the genome number.
Yeah, right. So I don't know if one is better than the other, but at least I present, here's all 3. So some of this we went over before, and probably I won't, but the number of components as you go up in dimensions gets to be very large, and really the only ones I've really seen are up to n equals 5, and that's the Kaluza-Klein metric, and I think someone's going to give a talk on that, so I'm not going to go over that. Most of the string theories have very large dimensions, 10, 11, and 26. But all the dimensions greater than 4 are curled up, and they compactify them, so they don't have this many equations to solve. So they always get back to the 4 something similar to the 4 dimensions that we did in class, because they usually compactify these other dimensions. However, there was one paper by Belushi, and he did not do that. He used a 4-rank tensor for curvature, just like we did, but he also used a 2-rank tensor for torsion. So he put the idea of torsion back in, so you have these 2 things, both curvature and torsion, that characterize in general curve, and he put actually both of them in. And then Polakov actually multiplied the metrics together, and again, the Einstein action here is a lot more complicated than the one that we had, but he basically multiplied the 2 metrics of the manifold and the world sheet. So this is the last thing on p-forms, and it's in actually Weinberg on page 113, and I won't go through it in detail, but just give you the basic result that there's a 1 form that's basically kind of like the dot product, a 2 form, which has a shape operator in, and sometimes people will call this a wedge operation, and curvature is basically the ratio of those two operations. So that's my conclusion. This is kind of a interchange between an engineer and a mathematician, and you can read it, but basically the bottom line is that mathematicians like to generalize, but physicists and engineers have to conceptualize. So that is the end of my presentation. If there's any questions.
Any questions?
Okay.
How does string theory come down to 2-dimensional gravity? You had the Polyakov, and I think maybe you can say a few more words. Because it looked like 2-dimensional gravity, right? And so.
Well, I don't know if that was a Polakov.
Yes, no, it was correct. We were told in the previous talk that actually there isn't too much dynamical going on in 2-dimensional gravity. So.
But he still has, the Polakov still has,
you might want to magnify that.
He still has, the 2 metrics, plus he's got these,
Can you make it readable?
Yeah.
So that's 2-dimensional gravity.
Yeah. Well.
Can you go through the terms? It does have a metric, right?
Yeah. Actually, it has 2 metrics there. One of the metrics is of the target manifold, which I think is the H, and the other metric is the standard G of the world sheet or the world line. Okay. T is supposed to represent the tension of the string.
Right.
The sigmas are the 2 dimensions, okay, and again, he had to assume something more complicated than the Einstein, because otherwise it would reduce to 0.
Right, but the H is basically what we describe as the metric in this class. So he's got 2-dimensional gravity, and then there is this X field, right? And that X field describes how this string
interaction,
string, which is in fact a world sheet, it's a string in one time in one space dimension, how that is embedded, right?
Yes.
Embedded in a higher dimensional space, right? So that's the X's are the coordinates in that higher dimensional space. So the action for string theory actually does involve 2-dimensional gravity in some form where in this particular case the embedding is represented by the type of scalar field that you were talking about before, right? Because that x is like the phi you were talking about. It looks, in this framework, it looks like a massless scalar. Right? But in fact, this is the coordinate of the worksheet embedded in d-dimensional Euclidean space. So there's lots of interesting ramifications, actually. Any more questions? All right, thank you so much.
Okay, well, I guess I get to be first, which is nice, because that means most of this will be forgotten by the end of the day due to the other presentations. So when we start with two-dimensional gravity, we have to be careful and explain, well, what do we mean by two-dimensional gravity? Because there's actually several different ways of interpreting this. So when we usually talk about two dimensions, we mean two spatial dimensions, such as flatland. But in relativity, we have to remember that time also factors as a space-time dimension. So spaceland is four-dimensional, flatland is three-dimensional, and when we talk about two dimensions, we can mean line land. So at first I thought, like, well, I can actually sort of cheat and talk a little bit about both line land and flatland. But then I remembered I only have 15 minutes, and some of my classmates here are going to be talking about different dimensions too. Whoops. So let's talk a little bit about the motivations, or why we would want to talk about gravity in dimensions other than 4. And the simple reason is the math is simpler. As an example, we can consider the independent components of the Riemann tensor. Whoops. In 4 dimensions, as we remember from class, the equations to determine the independent components of the Riemann tensor is given n equals 1 over 12 d squared times d squared minus 1. And they can be divided into the Weyl tensor and the Ricci tensor. So the great thing about lower dimensionality is that we can have fewer components. And in fact, when we're dealing with 2 dimensions, the only independent component that determines the curvature is the Ricci scalar. For comparison, we can go in the opposite direction, which I'm sure we'll probably see in some of the future presentations. If we add dimensions, then the components can quickly become more complicated. Now, why would we want to have the math be simpler? Well, simply put, it's a useful teaching tool. When we think about other fields of physics, for example, when we originally learned quantum mechanics, one of the first things we do is solve the Schrödinger equation in one-dimensional potentials. Because in a one-dimensional potential, you can, despite this being a simplified model, you can be introduced to the basic ideas of bound states, tunneling, and energy quantization. Or in, for example, statistical mechanics, in 2 dimensions, the Ising model allows you to have an exactly solvable system and yet be able to see things such as phase transitions. And it's also pretty nice in developing toy models for things like quantum gravity, where having a mathematically simpler model allows you to play around with different ideas in order to get a better grasp of some of the fundamental issues involved without getting slowed down by a lot of complicated mathematics. So how exactly do we do gravity in 2 dimensions? Well, one possible approach is we can just take the Einstein equations and then solve them in 1 + 1 dimensions. And if we do that, we will need to write the Riemann tensor in 2 dimensions, which will give us an expression that we can contract into the Ricci tensor. And when we do that, we realize that in 2 dimensions, the Einstein tensor vanishes identically. It's 0. So what does that mean? Well, it means that line is kind of boring, because if we remember the Einstein equation, this just tells us that the energy momentum tensor vanishes identically. So there is no matter in line land. However, since the Ricci scalar need not vanish, we can still have curvature, but that just means that we don't really have any constraints on it, and our curvature becomes somewhat arbitrary. So of course, the equation I wrote down is the one without a cosmological constant, so we can sort of bring matter back if we have one. But then we notice some strange things, such as if we require a positive energy density, then the cosmological constant has to be negative. And it really still doesn't solve our problems with curvature. So from this point of view so far, it looks like we're not in the best of shape when dealing with 2-dimensional gravity, right? But so we don't want line land to be that boring. So instead of using the Einstein equations, what we can try to do is actually build an alternative theory for gravity. And that's actually part of the appeal, because it means that we can't just take the Einstein equation and cut it down to 2 dimensions and have something interesting. So this allows us to sort of redo gravity, and this is a pretty interesting teaching tool then, because it can cover a lot of the sort of basics of general relativity really quickly without having to have some of the difficulties involved with the math. So there are different ways we can try to do that, and 2 of the ways we can go over. We can extrapolate a 2-dimensional general relativity from a Newtonian 2-dimensional gravity, or we can try to derive it from a principle of equivalence. So if we can do it from Newtonian gravity, we can try writing the Poisson. Okay, so we can consider the Poisson equation for Newtonian gravity, and this is it in 4-dimensional form. And so in 2 dimensions, we have something similar, but not quite exactly the same. Either way, the purpose is to get the appropriate equation of motion. And what we notice from this equation of motion, whether in 4 dimensions or in 2 dimensions, the trajectory of the particle depends only on position and velocity, and not on the mass or the matter. And whether in 4 dimensions or 2 dimensions, this can be an introduction to the idea that maybe gravitational effects is not in terms of mass, but coming from just an intrinsic property of space. So continuing from this line of thinking, we can basically transform away the effects of gravity through a freely falling reference trajectory. Yeah, and I apologize. Apparently, the formatting is being messed up, but
just say it in words.
Yeah, we define.
Everything we can read is actually the first entry.
Yeah, formatting's messed up. Sorry about that.
You could probably just pull it down. Just try to edit it right now.
I prefer not to. We can define a new distance that is basically the difference between an arbitrary trajectory and a freely falling trajectory. And if we require that distance to be small, because we're going to be dealing with local transformations, then we can, to first approximation, we can get sort of an acceleration in terms of something similar to a tidal force. And if we interpret this as a non-relativistic limit, we can interpret it as a geodesic equation, or an equation of a geodesic deviation. And then if we combine the two, we realize we have definition of these Ricci scalar as 4 times the gravitational constant times the mass density. And if we interpret this as a non-relative, so if we recognize this as the time-time component of an energy momentum tensor, we can consider this another non-relativistic limit of a new field equation. So we can say that in 2 dimensions, we have R equals 4g times the metric times energy momentum. And if we look at this equation, we see some of the basic features of general relativity as explained in simple English, that matter leads to curvature of space, and that in turn leads to gravity. So this is a pretty useful way of sort of introducing general relativity in a fast and concise way. So we can basically have some more fun with this, with the principle of equivalence. And the basic method of doing so is that we can start with the idea of a free particle in a free trajectory in flat space-time. So the mass density for such a particle is given by this function, and we can calculate an energy momentum tensor. And again, I apologize for my formatting. I don't know what's causing it. But
so the action has what I can't read is what is inside the
yes.
electron.
Okay.
Is it a box?
It's supposed to be a script L for the Lagrangian density.
Okay.
So for a free particle in flat.
So the next line is that script L?
Yeah, it's supposed to be a script L.
Is equal to minus?
Minus.
P.
It's supposed to be a rho for a mass density, because the Lagrangian density is supposed to be, for the free particle, the Lagrangian density becomes the mass density in its rest frame. So if we take this and so now we can consider that we can describe the effects of gravity as a field. So we can couple this to a scalar field. And we don't want to make any assumptions, so we can couple this to an arbitrary scalar field. And if we do so, we then get an action that is the sum of the different contributions of the Lagrangian densities associated with first the particle, then the field, and then that's supposed to be an interaction. So to mass the scalar field, we can, and the coupling, the Lagrangian densities, we can sort of get them just from an arbitrary scalar field phi, and then a coupling that is a function of that field. So if we use the Euler-Lagrange equations, we can get something resembling basic equations of motion. And again, those boxes are supposed to be script L's for the Lagrangian densities. And if we just go through the Euler-Lagrange equations really quickly, we can get a relationship between the phi and the coupling. And then this is where the equivalence comes in, because we're going to require that the energy momentum tensor can itself be a source for the gravitational field. And again, it can't really be seen due to a formatting error, but then we get a field equation that gives the sort of the D'Alembert of the field to equal to -2 times the gravitational constant times the flat metric times the energy momentum tensor. And the coupling, we can solve from the Euler-Lagrange equations and require that there's no coupling when the field is 0. We can solve the we can also solve a field equation in terms of the coupling interaction. And if we combine the two, we realize that we have, okay. So it's the same field equation as before. It becomes R equals 4g times the metric times the energy momentum tensor. And
so the source is always the trace of the energy momentum.
Yes.
Tensor, except here it's the trace of whatever you get for a scalar field, right?
Yes. So that means that this gives us a new perspective on describing gravity. We can consider it a curved space-time with a metric, with some arbitrary metric from the flat space-time given by the scalar field. And then that gives us the same equation from before. So just by working in 2 dimensions, we can sort of really quickly see that we have the point of view where the space-time is flat and the particle is interacting with a scalar field with an appropriate field equation. Or alternatively, we consider that space-time is curved and the particle is falling freely by the field equation R equals 4 times g times the metric times energy momentum tensor. So if we consider this in retrospect, we can see that we can have a simple toy model for gravity where we get an equation of constant scalar curvature. And the basics are that we have the same basic procedure for learning general relativity, but with simpler math. And going by this same logic, we can sort of do different things with it in order to, if we can solve, we can find solutions for more complicated effects in general relativity in order to see some of the basic concepts without going into some of the more difficult mathematics. And I'm basically out of time, so I'm open to any questions.
Well, thank you. So many questions.
Yes?
Can we get anything like singularity in two-dimensional?
Actually, yes. So it is possible to get something resembling a black hole solution within 2 dimensions. So if we can start with something similar to the vacuum solutions. Then we have R minus cosmological constant equals 0. Or if we can neglect the cosmological constant for a while, but then just add a point source. The exact solution for that actually does allow for the appearance of event horizons, which means that if you assume certain restrictions on the point source, for example, having a constant point source, it allows you to see event horizons. And one of the interesting parts is that you can actually get Hawking radiation from a 2-dimensional solution. So it's also a pretty interesting way to address like black holes, for instance, with general relativity.
Any other question? Do you have some reference on this work?
Yes.
What did you find useful there, so you might want to mention?
Okay, so yeah, that's a bunch of other. Let me see if I can actually. So the main references that I used. What I found particularly interesting was this paper by A.D. Boozer, or General.
Can you maximize it?
Yes. Yeah. What I found most interesting was the paper by A.D. Boozer, because it basically explained the approaches to general relativity, or like finding a model for general relativity in 2 dimensions. Also particularly interesting was a book, Lower Dimensional Gravity. It came from it's a revised version of actually Brown's thesis, which covered several different solutions for problems in general relativity in terms of 2 and 3 dimensions. And some of the other ones are papers I came across. So one of the subtitle jokes actually was the easy enough for an undergraduate to do. I sort of came up with that idea because aspects of general relativity in 1 + 1 dimensions was actually written by an undergraduate.